Hello. Hello. So, welcome to the stream, and this will be a short stream. We will solve, I think, one problem, and then we'll wrap the stream up because I have some work to do. So yeah, let's start. Hmm. And before that, let me erase this. I don't want to remove this snippet, so let it be here. Okay. What? Okay, so there is something wrong with the parser or linter, whatever it is. Okay, so we were solving this flight routes check. Okay, and yesterday I told that this problem will require a special algorithm called cses algorithm. Okay, so we will look at that today. So flight routes check. Flight routes check. Okay, so we have this problem. We are given entities and flight connections. Our task is to check event travel using the available parts. Okay, output is if all routes are possible, no, otherwise you also have to print two cities that you cannot travel from A to B. If there is a possibility, flights are one-way flights. That is the major thing that we need to consider. Okay, flights are one-way flights. Otherwise, we if the flight was not one-way flights, we could have checked only. We only needed to check the components. Okay, if there are multiple components, then that means we cannot go from one to another. But in the directed case, even if we can go from one one node to another, it does not mean that you can come back from that, right? Because we don't have the luxury of that two-way connection like in the undirected mode. Okay, so let's create this graph here. So one is connected to 2, 2 is connected to 3. Okay, 3 is connected to 1, 1 is connected to 4, and 3 is connected to 4. Okay, so we can see that we can reach 4, but we cannot go from anywhere, go to anywhere from 4. Okay, because it has only incoming edges. So how do we check, how do we solve this problem? So okay, before that let's go through that cses algorithm. Okay, Kosaraju algorithm. Okay, so this is very simple actually. It has 3 steps. First is we will sort the graph or nodes topologically. Okay, then what we'll do is run a DFS in reversed graph. Okay, run a DFS in reversed graph, and while we are doing this, we'll also assign the groups. Assign groups. Okay, and the third is now that we have different groups, they are basically different components which are strongly connected in itself, and if we connect those groups, then we have a strongly connected graph. So we can choose any two nodes to give the answer in case of no, like if we have we need to return the two nodes also, right, that we cannot travel to or cannot travel to and from, so we will need that in that scenario. Okay. What was the third step? Forward. First step is done. Topological sort is done. Okay, let's try to understand with an example. Okay, suppose I have a graph like this. Okay, 4, 5, 6, and then I have 7. So is it possible to reach 7 from 1? Yes, it is possible. But is it possible to reach 1 from 7? No. So you can see that it is not a strongly connected component, right? But it is a connected component because we can reach to 7 from 1. Or matter of fact, we can reach every other node from 1. Okay. It is connected but not strongly connected. Okay. So how do you solve this? Basically, we will do these types. Okay. So sort the nodes topologically. We can do a simple DFS with a stack to achieve that, or we can do Khan's algorithm or anything. But for this problem, we'll stick to DFS only. Okay, we don't want any unnecessary overheads of queue and arrays of like integers and all. Okay, so we will do that. We will solve using DFS only. So we will keep a stack with us. Okay, and we'll start DFS from 1. We'll start the DFS from 1. We can I think should start from 1 only, or we can start from any node also. Yeah, we should cover every node, but we start DFS from 1 for now. So we will start from 1. 1 will go to 2, then 3, then again 1, and then 2 will go to 4. 4 will go to 5 and 6, and 5 will go to 7. So yeah, the first node that we will reach in DFS will be 7 only. 7 we will put 7 in the stack. Okay, after that we will backtrack, and then the other node will be 5, I think, then 6, then 4, then 2, then 3, then 1. Okay, now that we have this topologically sorted stack basically, so we will start DFS in the reversed graph. Reversed graph will be like this. Here and then here, then we have this, we have this, we have this, and we have this. Okay, so we start from 1. So when we do DFS, 1 will go to 3, then 2, and then 1 again, and this part will be done. So you see, we cannot travel to this part of the graph, so that must mean that means that this must be a strongly connected component in the graph. Okay, and since we started from 1, what we'll do is we will call this whole SCC or group as 1. Okay, this is basically a representation of it. And then since we have already visited 2 and 3, we will not process it. Now it comes to 4, so we will start from 4, go to 6, then 5, then again 4. So we could not reach 4, right? So this will again 7. So this will be another strongly connected component, and since we started from 4, we'll call it 4. Okay, and yeah, it's the last node will be 7. So 7 will be another strongly connected component. So you see, we have 3 groups. One is called 1, other is called 4, and the other one is called 7. So how many edges do you think we need to make this graph a strongly connected graph? We would only need 1 and 2 edges to make it a strongly connected graph. Okay, 2 edges to make it a strongly connected graph. And the thing is, if we have multiple such groups, then that means we cannot travel from one city to another. So we have our answer. Okay, and also if we cannot reach, then the 2 nodes that we are not able to reach are also here. So we cannot reach 4 from 1 or 1 like that. Okay, we cannot reach the answer will be here 4 2. Okay. So we can do something to print the answer also, print the nodes where we cannot reach. Okay, so yeah, that is the basic so those are the steps to those are the steps for cses algorithm. And the third is I think process the groups actually. Maybe, I don't know, I'm just making the third step up. So yeah, we do DFS here, get the top sort, run a DFS again in the reversed graph, get the SCC and its pre-representation, and then we'll do like whatever we want to do. Okay, so let's try to implement it. First let me copy the input, and we won't be needing DSU, so instead we will need we will be needing we will need DFS. Okay, should I make a DFS inside this? Okay, there is no harm in doing that. So okay, we will need an adjacent, also reverse adjacent, and okay, and now adjacent we have this ready. Okay, we will need a stack. Tape top sort. Okay, we will also need a function basically ll, and okay, basically void ll. We will call it dfs1, and it will be capturing the function how did we do it yesterday? I think it was in this one. No, which one? This one, I think. Ampersand LLRC. Okay, LLSRC, and can if we'll also need visited array, and we also need another visited array. Here we'll do is 1, src is true, and for auto node and adjacent src, if not with 1 node, then we'll run a dfs again, and after we are done we will just put the src here in the stack to get the topological sort. So this is the first step. Get the topological sort. Second step, run the DFS in reversed adjacency list and assign groups. Okay, so we will have a count of how many SSCs we have. We'll also have groups themselves. Okay, group, it will be n plus 1, and initially what we'll do is we will put 1, assign 0 to every node. Okay, and we have done that and that. Okay, we will need another DFS. So here we'll run DFS, or rather function I from 1 to plus 1 if not with 1 I, then we'll do TFS 1 I. Okay, and here we will do this while st.empty. We have the topological sort and we are running from that only. We are going to iterate in topologically sorted order. So it will be top, and for this we are going to run the DFS. DFS or BFS, does it matter really? If vis2 for node is visited, we will just continue. Otherwise, for auto node in RADJC current, we are going to do this. If not vis2 node, then we don't need this. Okay. Done. Otherwise we will just run DFS2 from the current. This is sorted. Okay, we need one more thing. So LL representation. So we will send current only. Should we? Let's see. Okay, we're done here. So that we have a group. We will just increment count, and if count is greater than 1, that means then okay. So if count is double equal to 1, then we can travel. Otherwise we need to print no, as well as two nodes that we cannot travel, or two cities that we cannot travel. Okay, so we will choose any two groups. Okay, so int a, lla. For that we will run, we will iterate through the groups. We will set a and b to -1 initially. If a is set to -1, a will be equal to I, else if b is double equal to -1, b will be set to I and will break. And here we will check. What will we check? If adjacency a dot find b, in that case we will print b a, otherwise it should work. VBC, where is VBC? Okay, so find for what? Find in vector. Count. Okay, so I'll use count. So if count all ADGs a the value of b is greater than 0, standard count. Yes. That's strange. Why? Why am I getting yes? Let's try to make another test case for us. C. Yes. Again, yes. Okay. No, 0, 1. Why 0? Okay. Not auto in group. This should work. 1 1. No. 4 1. Okay. 1 4. We cannot go 1 4. But we can go 1 4. We cannot go 4 1. Okay. We don't need this, and any one will work, right? So okay, this should work. I'm not sure. Please. Oh wow, sweet, very sweet. It looks pretty cool actually, this code, you know, simply because I've used these functions. Okay, on to the next. Planets and kingdoms. And planets and teleporters. A, B belong to the same kingdom when there is a route from A to B and B to A. Your task is to determine for each planet its kingdom. Oh, yeah, it's the same question. Okay. So, planets and kingdoms. Let's go to the board. The same Kosaraju's algorithm will be applicable here also. Planets and kingdoms. Okay, same Kosaraju's algorithm will be applicable here. Kosaraju algorithm. Okay, again the same steps will repeat, and this time we need to return that representation array. Okay, so if I let me copy this, I've copied it and paste it here, and let's draw this graph. 1 is connected to 2, 2 is connected to 3, 3 is connected to 1, 3 is connected to 4, 4 is connected to 5, and 5 is connected to 4. Something like this. Okay, so again this is a strongly connected component, this part, and this part is a strongly connected component. Okay, so 1 and 4, 1 4. So we in the representation we just need to return the we don't need to return the okay, so the answer is very simple. What does 2 mean? Number of kingdoms. Okay, so we just need to count the strongly connected components. So this is the first component and this is the second component, and we will return the representation array. Okay, so let's remove what we don't need. We don't need this. Also here instead of sending the current, we should send the count here. Okay. The count will be 1 initially, so We will send count and count plus plus. This should work. And in the end, we'll return the count and also the group. Of course, we don't want the groups to be starting from 0, so we will change it a little. And y3, so 0. Okay, sorry, no, the answer is not what I expected to be. Done. Okay, this should work. We did not do any major change to the code. So this should be accepted. Giant pizza. Okay, this is I have not done in the previous graph practice session also, so I might need to solve this again. Devolution sequence. Okay. So all this will solve in the later streams. Okay, so for today I think 2 problems is enough, and let's wrap the stream. And yeah, thanks for joining in, and till the next stream, I hope you have a